Hello everyone. So today we'll be discussing on the topic Djkstra algorithm, right? So previously we had discussed on the topic DFS and BFS algorithm. So let's continue with the uh, let let's continue discussing the Djkstra algorithm, right? So let's get into the definition part here. So what does the definition part say here? Djkstra algorithm finds the shortest path from the given source node, right? So mainly just remember this, it finds the shortest path from the given source node to all other nodes in a weighted graph, to all other nodes in a weighted graph with non-negative edge weights, right? So with non-negative edge weights, so we cannot consider negative edge weights, right? We have to go with a this one, positive edge weights. So right, so this one we have to keep in mind when it comes to this Djkstra's algorithm. So Djkstra's algorithm finds the shortest path from the given source code to all other nodes in a weighted graph with a non-negative edge weights. So it uses what does it use? Basically it uses the greedy approach and the priority queue, right? So minimum heap, it uses the greedy approach and priority queue to always pick the vertex with the smallest distance, to always pick the vertex with the smallest distance, right? Let's move on with the explanation part, man. So we will start from the source node with a distance 0. What we'll do, we'll start from the source node with a distance 0, right? First we'll start from the source node with a distance 0. Next what we'll do, we will use the priority queue to always select the node with the current smallest distance. Again, we will use the priority queue to always select the node with the current smallest distance. For each neighbor, if a shorter path is found via the current node, we will update it. For the each neighbor, if the shortest this one shorter path is found via the current node, then we will update it, right? So we'll continue until all the nodes have been processed. So we'll continue the same thing until all the nodes have been processed. So this works on both directed and undirected weighted graphs with the non-negative weights. Again, so we cannot go with a non-negative weights, right? So we have to go with only the this one. We cannot go with a negative weight. Sorry. This works on both directed and undirected graphs with a non-negative weight. Just remember this one, right? So this is just the visual representation of the graph that will be considering this one as example, right? So I can just see here 0, vertex 0, 1, 2, 3, right? For 0 to 1 edge, we have the weight 4. For 1 to 3, we have the weight 1 here. From 2 to 3, uh, yeah, from 2 to 3 we have the weight 5 here, and from 0 to 2 we have the weight 1. So this is the directed graph, right? So you can see the arrow mark here. And also from 2 to 1, so here 2 to 1 we have this one alternative shorter path, nothing but here in this case it is 1, right? See here 0 to 1 weight 4, that's what I said. You can just go through it, right? You can just go through this one. You can just pause the video and have a look into it. Now this is fine, man. Now let's do one thing. Whatever we have discussed now within the explanation, the same thing let's articulate in the form of code, right? So let's try to articulate the same thing in the form of code. First thing, let's import the heap queue just to use the priority queue, nothing but min heap, right? So I'll just go with import here heap queue. This is fine. The next part would be let me go with def. We are going with a Dijkstra's algorithm, right? Dijkstra. So I'll just go with graph and start as the parameters here. This is fine. Now let's go with the number of vertices in the graph month. So let me assign this one to the n equals length of. Let me pass the graph here. This is fine. Simple. Till now, it's fine, I believe. Next, what shall we do? Let's initialize all the distances as infinity. Initially, let's initialize all the distances as infinity. So I'll just go with here. Um, Distances here. So this will be, let me go with float. We are initializing all the distances as this one, distance as infinity, right? So I'll just give here infinity as we are making use of the Python here, inf, right? So into n. We have successfully initialized all the distances as infinity. Next part here would be, let's consider the distance to source node initially as 0. Initially as 0. So let me give here distances of start. Let me initialize this one to 0. This is fine. Now what we have done here, so I have to consider from here, yeah. So this was the indentation problem. Sorry. Yep. Let me do one thing. I'll just come here. Yeah. Let me hit the enter here. Yep. Now we have successfully initialized all the distances as infinity, and we went with the distance to source node. We have successfully initialized that one to 0 as well. Now let's do one thing. Let's make use of the priority queue or the min heap. So let's go with the minimum heap uh, to store the this one, which stores actually distance comma vertex, right? So I'll just consider PQ, nothing but the priority queue here. So this one, let me give 0 comma start here. This is fine. Simple. Till now, I hope this is clear. Very easy, right? Let's go with the while loop here. So while of priority queue. So within the while loop, what we will do? First, we will pop the node with a very small distance or smallest distance, right? We'll pop the node having the smallest distance. Just remember this one. This is very important. First, I'll just go with here current distance. I'll just give dist here. Also, u equals, we are popping right here. So I'll just go with heap q here dot, we are popping the smallest this one. Let me go with heap pop here, that power this one Python provides, and let me pass pq. This is fine. Now let's do one thing. If this distance is outdated, then we have to skip it, right? If this particular distance is outdated, then we have to skip it, right? So let me go with if uh, current distance, if it is greater than, so let me go with here current distance is greater than distances, right? So we have already considered distances of u. Then what we will do, then we have to skip, right? So I'll just make use of the continue keyword that the Python provides, right? So this is fine. Now we have successfully popped the node within the smallest distance, or also if the particular distance is outdated, then we have to skip it. These two things we have done within the while loop. Now we have to explore the neighbors as well. We have to explore the neighbors as well, right? So let's explore the neighbors, meaning let's move on with the iteration part here. So I'll just go with neighbor here. Also, let me go with weight in graph of u. This is fine. The next step would be, so within this, within the for loop, basically we have to calculate the new possible distance, right? So to calculate the new possible distance, I'll just go with a new dist here, variable name. So this will be current distance plus weight. This will be current distance plus weight, right? So this is fine, man. If found, so if we have found a shorter path, then we have to update it. We have to update it. That we need to do. I'll just go with the if new distance less than this one. What do we call? Distances of neighbor. Let me give you distances of neighbor. Then what we need to do here? Then what we need to do? I'll just go with the distances here. Distances of neighbor. So this one, let me assign this one to the new distance one. I'll just go with new dist, right? So this is fine. Now let me go with the heap queue dot heap push. Uh, this is fine. Push of priority queue, comma. I'll just go with new distance, comma neighbor, right? So neighbor. So this is fine, man. Yep. Finally, let's do one thing. Let's return the distances. We are calculating the distances, right? So we have to return the distances. So this one second. Did I get confused? No, right? So I'll just go with the return. Yep. So here is the distances. Yeah. We are done with the coding part, or we are done with the algorithm basically. Now let's go with the example graph, right? So let's go with the example graph here, or example usage. So let's go with a graph that is represented as the adjacency list, right? Each list element is equivalent to, so this one we are considering neighbor as well as the weight, right? So I'll just go with graph here. So this one, let me go with 1 comma 4 comma 2 comma 1. So this one second. So this one, let me give this one within the square bracket actually. Right? So this is fine. The next one, so this is these are the edges from node 0, right? So 1 comma 4 and 2 comma 1, whatever I've given, right? So this one, let me go with 3 comma 1, right? So these are the edges from the node 1 actually. Now let's go with the edges from node 2. From node 2, let me go with 1 comma 2 as well as 3 comma 5, right? So this is edges from the node 2, right? So finally we have to go with the edges from the node 3 as well. I'll just give here empty, right? So this is fine, man. Now, uh, yep, let's go, or let's start from the vertex 0. I'll just go with result equals, let me give Djkstra here. So this one I have misspelled Djkstra. Where it is? Yep, correct this one. Djkstra of this one. What we need to do? Let me pass graph as well as the 0. So we are starting from the vertex 0. Now let's print the final shortest distances. Let me make use of the print statement here. So this one is shortest distances from source 0. Shortest distances from the source 0. This one, let me pass the result. Let me pass result here. This is fine. Now, yeah, I hope, yeah, we are done with the coding part actually, right? So so the output that we need to get here is shortest distances from the source 0 is 0, 3, 1, 4 basically, accordingly with the example that we have considered, or the graph that we have considered here, right? So here, let me run the code. We have the idea on the algorithm, so I have explained step by step, right? So whatever we have done, so I'll just go with this one, file name. Let me run the code, whatever we have written, right? So I'll keep Control J here. What is this one? Yeah, let me give Python file name dot py. Yeah, shortest distance we are getting from the source 0 is 0314. We are getting the correct output basically. So let me explain whatever the this one basically output, why it is the shortest distance from the source 0 is 0314 here. So from the node 0, the shortest distance from 0 is 0 itself, right? So this one, let me show you correctly actually. This one is from node 0. So this one is from node 0 actually. This is from node 1, node 2, and node 3, right? So these are edges from node 0, node 1, node 2, node 3. Line number 65, 66, 67, and 68 I'm speaking of, right? So edges from node 0, 1, 2, and 3. This is fine. Now what we need to do, basically, so uh, shortest distance from 0 is 0, right? Source itself. And when we consider node 1 actually, accordingly with the diagram, when we consider node 1, see, from the node 1 actually, the shortest path is 3, from 0 to 2 and 2 to 1, right? So let me write here. So let me consider like this. So suppose this is node and this is shortest distance actually. Yeah, this is shortest distance from the node 0 actually. From 0 actually. Let me give here from 0, and the final one is this one. What do we call? Path taken. So the final one is path taken, right? So these three things. So node, let's consider here 0, 1, 2, and 3, right? So the shortest distance from 0 is, so from 0 it is 0 itself. From the node 1 it is 3, accordingly with the example we have considered. From this one, what do we call? From 2 it is 1, right? So from 2 it is, the shortest distance from 0 is 1. From 3 it is 4 basically, right? So the path taken, this one, source itself, 0 itself, I can just write here 0. Then from this one, from 1, node 1 it is 0 to 2, 2 to 1 basically, right? From this one 2 it is 0 to 2, it is 0 to 2, right? So from node 3 it is this one from 0. So let me represent here from 0 to 2, 2 to 1, then 1 to 3, right? So here, let me tell you how the algorithm works here, basically, right? So we will start from the node 0. We'll start from the node 0, this one, right? So distance is equivalent to the 0 initially. Distance is initially it is equivalent to the 0. And we are visiting the neighbor 2, where the neighbor 2 cost is 1, right? And this one. And the cost of 1 is 4, basically, right? So we'll do that. The second step, we'll visit the neighbor 2. Cost of this one, what do we call? We are visit this one first. We'll start from the node 0, distance 0. We will visit the neighbor 2, cost equals 1, and we will visit 1, cost equals 4, right? So we'll visit 1, we'll visit 2, cost equals 1, and we will visit 1, cost equals 4, basically, right? So next, node 2 becomes the next, right? Node 2 becomes the next, right? So now minimum distance is basically 1, right? So minimum distance is basically 1 now. So from the node 2, path to 1 is equivalent to 1 plus 2 here. From the node to path to 1 is 1 plus 2, that is equivalent to 3. That is equivalent to the 3. So this is the shorter path that is found, right? So we will be updating this one, right? So the next step would be we have to consider node 1. Node 1, the distance is 3. From here, path to 3 is nothing but 3 plus 1, which is equivalent to 4, right? So this is for the node 1, right? So this is for the node 1, basically. This is fine. From next, let's consider the node 3 here. Let's consider the node 3. Node 3 updated with the 4. Node 3 is updated with the 4, and now the algorithm finishes. Now the algorithm finishes, basically, right? So this is about it for the algorithm, right? So this, we are making use of the greedy approach, right? So mainly we are making use of the greedy approach here, right? So this is it for the algo. So the output that we are getting here is 0314, which is absolutely correct. We are getting the desired output, right? As per the algorithm. Now we are done with the Dijkstra's algorithm, right? So let's do one thing. Let me quickly summarize whatever we have learned so far, right? So now, first of all, just keep these things, right? So these 4 to 5 points in the mind. This is important. The algorithm uses, basically Dijkstra's algorithm make use of this uses greedy technique, right? So this makes use of the greedy technique. Just remember this. So let's discuss the use cases as well. So use case of the Dijkstra's algorithm is to find the shortest path from the one node to all others in the weighted graph, from one particular node to all the other nodes in the weighted graph. Here in this case, we have connected from the node 0 to all, right? So mainly use case here is to find the shortest path from the this one. Basically, we have found the shortest path from the node 0 to 1, 2, 3, right? Here in this case, to 3, 4, basically. Right, so this is fine. 1, 2, 3. This is fine. We are finding the shortest path from the one node to all others in the weighted graph. This is the use case. So basically, the data structure that are being used here is priority queue, right? So we made use of the priority queue, nothing but the min heap. We went with the min heap. Also, what is the time complexity here? The time complexity of the algorithm would lead to big of vertex plus edge, v plus e, right? Into log v, into log v, into log v. Vertex plus edge into log v. Finally, the space complexity would lead to big of v as well. So this is the time complexity and this is the space complexity, right? The time complexity would lead to big of v plus e into log v, and the space complexity would lead to big of v man, right? So let me delete this one entirely. So these are some of the important points that I had to mention, that or that I found it will be very helpful. So I had to discuss, right? So this is fine, man. We are done with the Dijkstra's algorithm, right? Mainly Dijkstra's algorithm efficiently finds the minimum distance paths from the single source to all the vertices using the greedy method combined with the priority queue data structure. Just remember this one. Whenever you hear Digistra's algorithm, all you in your head, it should be we are finding the minimum distance path from the single source to all the vertices, right? And the thing that you have to pop up in your head is that has to pop up in your head is we will be going with a greedy method as well as the we'll be making use of the data structure priority queue. These things has to pop up whenever you hear this one, Dijkstra's algorithm, right? So we are done with the algorithm. Next, we'll be discussing on the topic Bellman-Ford algorithm, right? So Bellman-Ford algorithm is the extension to the Dijkstra. You can take it in that way. Only difference is along with here, we cannot uh, go with the negative weights, right? Here, see here. Works on both directed and undirected graphs with the non-negative edges. And the Bellman-Ford algorithm, we can also go with the this one negative weights as well, right? So that's the only difference. Now only I'm telling, right? So this is fine. So we're done with the distrust algorithm for now. This is it. Thanks for watching, guys.